In number one, we have a square and we have a couple of special properties of squares. So I'm just going to write them down over here. So number one, squares are equilateral. So that means all of the sides are equal to each other. Number two, squares have opposite parallel sides. So this side and this side are parallel. This side and this side are parallel. Number three, all the angles are right angles. So right angle, right angle, right angle, right angle. Number four, the diagonals are congruent or the same as each other. And number five, diagonals are perpendicular. That means where the diagonals meet, they intersect to form 90-degree angles. We are looking for which statement is not true. So three are true, one is not true. AS, perpendicular to SH. AS, SH, they do meet to form a right angle. That's true. AS, parallel to CH. AC, parallel to SH. True. AH, this diagonal, perpendicular to SC, this diagonal. True. SH, perpendicular to AC. SH and AC are not perpendicular. They're opposite. They're parallel. That is the correct one. Please make the correction to number two if you didn't already. There should be a 1/2 there in that answer choice. We have an angle bisector. That means it splits the angle equally into two congruent parts. We're looking for the statement that's not true. So three are true, one is not true. Measure of angle EBF. That is this one here. E to B to F, right here, is equal to measure of angle ABC. ABC. ABC is the whole big angle, A, B, C, B in the middle. So the vertex is at B, A, B, C. So this is half of this. So that's true. Let's reset. Angle DBF, this one, is half of angle ABC, ABC. This is half of the whole angle. So that's true. Let's reset. Angle EBF is equal to ABC. ABC, this whole angle here. These are not equal. This is half of this. That's the choice we're looking for. Answer choice 4 says DBF, this one over here, is equal to angle EBF. And that's true because those are both halves of the whole angle. So that's true. A is the center of one circle and B is the center of another. So from A to any point on the circle is the radius. From B to any point on the circle is the radius of that circle. We're focusing on segment AB. Just to make it a bit clearer, in circle B, AB is a radius of that circle. In circle A, AB is also a radius of that circle. So AB is a radius of both circles. Both circles are the same size. Remember, all radii in a circle are the same as each other. So segment AC, from the center to a point on the circle, that is a radius of circle A. Segment AE, another radius of circle A from the center to a point on the circle. Now BC, that's from circle B. Here's the center. BC is a radius. CD is not a radius. It's a chord. It just goes from point to point. It doesn't pass through either center. DE is not a radius. DE is once again a chord. It doesn't pass through either center. In order to be a radius, it has to pass through a center of the circle. So AC, AE, and BC all have the same length as AB. The construction that we have here, number 4, is the construction of an angle bisector. So angle BAC got bisected. So this piece, angle BAE, is congruent to this half, angle DAE. 2 equal halves due to the bisector. A says EF is the bisector of angle BAC. Absolutely true. That's exactly what this is a construction of. It's the angle bisector construction. B. Line EF is the perpendicular bisector of segment BA. Here's EF. Here's BA. Those are definitely not perpendicular to each other. And this is not splitting this in half. EF is the perpendicular bisector of AC. These are definitely not perpendicular to each other. EF is the perpendicular bisector of segment BD. That's true. EF is parallel to CD. Absolutely not. B and C are the only true statements here. Sorry, I said B and C. A and D, the ones with the check marks, are the only true statements here. JK is an angle bisector. So the two halves are equal to each other. So the 6x plus 2 part is equal to the 8x minus 6 part. Inverse operations. Our goal is to isolate the term with the x. And our x value is 4. Now we need to find the value of angle LJM. LJM, that's this whole angle, both pieces together. Let me plug in. And since this is a bisector, both halves are equal. 26 plus 26 is 52 degrees. We have line segment AB. With C in between A and B. AB, the whole line segment, can be represented as 2x. BC is x plus 6. and AC is 24. If I put these two pieces, AC and BC together, I get the whole thing AB. So I'm going to make an equation that says that. If I put the 24 piece of the line segment and the x plus 6 piece together, I get the full line segment, which is represented as 2x. I'm going to combine these two like terms, and I'm going to subtract x from both sides to isolate the x. I'm going to plug in here in order to find the length of BC. 30, the x value, plus 6 is 36. And if I plug in here, 2 times 30 is 60. So notice how point C is not the midpoint of the line segment. It does not split it equally into two equal parts. Both parts are unequal. First, let's start off by splitting the line segment into two equal parts. That's going to be a perpendicular bisector to split it equally to find the midpoint. Let me get some more space. Put my compass on one endpoint. Open up to the other. Swing a circle or an arc, it doesn't matter. Swing another circle. Same radius on both. There should be two spots where your circles intersect. I'm going to do that better. I'm really bad at using the straight edge. Now we have two equal parts. This is the midpoint, and I'll just label it with an M of AB. And we have two equal parts due to the perpendicular bisector. So now, in order to get four equal parts, I'm going to split each half in half. And that should take me from 2 parts to 4 parts. So I'm going to do the same construction, but the endpoints that I'm going to use are the endpoints of a half of the line segment. So I'll start off by doing this side from A to the midpoint. Same thing on A, measure to M, make an arc or a circle, head on over to M, the other endpoint, same thing. Right through the intersection points. We have our perpendicular bisector. This point is the midpoint of AM of this half. These two halves are equal. Now we just need to split this half, BM or MB, in half as well. Going over to one endpoint, opening up to the other. Let me use a different color here so it doesn't get so confusing. Circle. Same circle. Through the intersection points. Here's our perpendicular bisector. Two equal parts. Now we have 4 equal parts in total of our original line segment. Two valid conclusions that I can draw from this construction. There's many. I'm going to say AM is congruent to BM because they're two equal halves, two equal parts. Once again, there's many valid conclusions. And I'm going to say I'll call this perpendicular bisector L. I'll give it a name. I'm going to say line L is perpendicular to the original segment AB, because when they intersect, they do form right angles. I could also say that M is the midpoint of AB. I could say this point is the midpoint of AM. I could say this point is the midpoint of BM. Many conclusions you can draw here. These are right angles over here as well. These are right angles over here as well. Lots of conclusions. We're making a perpendicular line through a point. Let me grab my compass from above. We're going to start off by putting our compass on the point that we want the line to pass through. We're going to swing an arc. You could make a full circle, but really the only thing that matters is that we hit the line in 2 spots, but you can make a full circle if you absolutely want to. Using the same distance, and it's okay if you switch the distance a little bit. Just whatever you do here, you have to do here as well. I'm just going to use the same one I was using before. Circle on one intersection point. Go to the other intersection point. Make the same circle. Where those 2 circles intersect, draw your perpendicular line. This new line passes through point P, or should come really close to passing through point P, and is perpendicular to the original line. Keep in mind this is different from the perpendicular bisector construction in the last question. This perpendicular line does not bisect the line segment. It doesn't have to bisect the line segment. All that this construction does is make a perpendicular line through a specific point. Nothing about bisecting. Bisecting is the earlier construction, perpendicular bisector from the previous question. Now we're adding to this construction, and our goal is to take this and to end up with, instead of a perpendicular line to P, to also have a line parallel to M passing through P. So it should go like, just to illustrate it, it should be something like this, parallel to the original. But we have to actually construct it, right? We can't just say that we want to do this. I'm going to go back on point P, and it might be helpful if you turn your paper sideways. And I'm going to just repeat the steps. I'm going to make another perpendicular. And let me talk about the justification for this before I actually do it, why we're making another perpendicular. We did speak about it in class. So this is what we have already. We created a perpendicular line to a line that we already had. If we create another line that's also perpendicular to the same line, that ensures that these 2 lines are parallel, because 2 lines perpendicular to the same line are parallel. And that's why we're making another perpendicular line. I'm on point P. I'm going to do the same thing. I'm going to make another arc. It doesn't matter the size. It just needs to hit the line segment in 2 spots. And mine doesn't. So I'm just going to extend with my straight edge. My previous line. So that way, I can see those 2 spots where my circle intersected. Once again, you don't have to make a full circle. You can just make arcs. I just made a full circle this time. Okay. On one intersection point, I'm using the same distance as before. You could swing a circle. And on the other intersection point, we're going to swing the same circle. It gets a bit messy. So I'm going to use a different color to indicate where the circles intersect. And right through those intersection points. Sorry, I'm terrible with the straight line feature on the computer. There we go. Now it's through the points. And notice how the line that we ended up with now is parallel to the original. And I know that for absolute certainty because we made this line, M, perpendicular to the purple line. And we made this blue line perpendicular to the purple line as well. And two lines that are perpendicular to the same line are parallel. And we talked about C. Let's make a hexagon. You can draw in a radius or measure the radius. Remember, the radius is from the center to any point on the circle. And I'm going to do this with the way that we did in class. Let me just mark that so I could see where to put my compass. I'm a tiny bit off. Give me one sec. I'm going to draw in the radius because this compass is not super accurate on the computer and I want to be as accurate as possible. Okay. Let me try to get that measurement again now. I think that's as accurate as I'm going to get. I'm going to go over to where the radius touches the circle. And I'm swinging a circle. That's the length of the radius I just measured. There's an intersection point here and one here. We're going to go over to both. It doesn't matter the order. I'll go down here first to where the circle intersects the first circle. Swing another one. Where it intersects the first circle is where we're going to go to now. And we're going to end up with 7 circles in total, 6 equally spaced ones around the original circle. So you're looking for where your new circle intersects the original circle. That's what you're looking for here. One more. Looks pretty. We have 6 intersection points. You could think of them as the flower petals. And if you connect all 6 of them together with your straight edge, you'll end up with a regular hexagon. We know that it's a regular hexagon because we created it with 6 equally sized circles. All of the circles that we created had the same radius. So that ensured that all the sides were equal. Now let's say instead of making a hexagon, you needed to make an equilateral triangle. Instead of connecting all 6 intersection points together, you would instead connect 3 of them every other. And that gives you an equilateral triangle inscribed inside of a circle. If it says inscribed inside of the circle, it does need to be this equilateral triangle or one made by connecting 3 of these intersection points, because notice how the vertex points are touching the original circle, and that's what you need if it says to make one inscribed in the circle, because the hexagon said inscribed in the circle as well. Notice how the vertex points are touching the circle. So you can't just make any equilateral triangle if it's described in the circle. The vertex points need to be on the circle that you began with. Let me bring my compass down. We're constructing a square inscribed in the circle. I'm trying to make a diameter, but I'm not doing a good job. There we go. Now that I drew in a diameter with my straight edge, that diameter is one of the diagonals of our square. And remember, diagonals of a square are both congruent and perpendicular. So I'm going to perpendicular bisect this. That's the construction that makes sense if we're going for congruent and perpendicular. I'm going to open up to the length of the diameter, swing a circle over to the other endpoint of the diameter. We're going to swing the same circle. Let me grab a different color. Right through those intersection points is where I'm going to draw my perpendicular bisector. These lines inside the circle indicate the diagonals of the square. So if we connect where those diagonals meet the circle, we can get the four sides. Oops. This is the hardest part with the straight edge. We can get the four sides of the square. I know that my construction is a square because the diagonals are both congruent and perpendicular since I created a perpendicular bisector construction. The last thing I want to show you guys in this video, oh, there's more. Never mind. Let's construct a line of reflection. Remember, the line of reflection is an equal distance between both of the figures. I'm going to connect two corresponding points together. I just connected B and B prime. I don't know why. And I'm going to make the perpendicular bisector. So I'm going to open up to the other endpoint, swing a circle over to the other endpoint, swing the same circle. That should be the line of reflection. But in order to be even more accurate, we're going to do it one more time for another set of corresponding points. It's going to be a tough one because it's such a small line segment. On the computer, those are tough. Too big and too small is tough on the computer. Okay, swing a circle. Same circle. And notice how it's the same line of reflection. That tells us that we found the correct line of reflection originally. Doing it twice with two pairs of corresponding points makes it more accurate. This one's going to take a few because we have to do a lot of perpendicular lines through a point. Let me start with the ones furthest away because they're harder. I'm going to start with A. I'm going to put my compass on point A. And the exact distance doesn't matter. but I do want to make sure, oops, that's not going to hit in 2 spots. I need to make it bigger. I do want to make sure it's going to hit the line in 2 spots. So I hit in 1 spot. I'm going to extend the line with my straight edge slightly. And that way I can see the intersection point here and here. I'm going to use the same color so you know it's part of the same construction. Then over to the other endpoint. And we're going to swing the same circle. And right through those intersection points, we have our perpendicular line. And that's where point A prime is going to go. It travels perpendicularly an equal distance across the line of reflection. That's what the reflection does. Okay, we're going to do it for, I'll do it for B now because B is second most complicated. C is easier. Use a different color. I'm going to use blue. Once again, I got to hit the line in 2 spots. I can't see where it hits, so I'm going to extend slightly. And I see that it hits the line here and here. And yes, this is going to get messy. I'm going to go over to one of those intersection points, swing the circle. Then, without changing my compass distance, other intersection point, swing the same circle. Right where those 2 circles meet, going to draw it in. And that's where B prime should go. As if this wasn't already messy enough, we're going to do it one more time for point C. This one should be the easiest because it's the closest. Oops. I'll be able to use a relatively small distance. Oh no, it keeps going everywhere. Sorry, I told you guys that with the computer, this is really hard. Right? I'm gonna go over to one intersection point, circle, sorry, my computer's being weird. Other intersection point, circle. We can draw our perpendicular bisector through. And there's C prime. In a different color, I'm just gonna connect the triangle points together. I'll do yellow, so it's brighter. And notice how it's the reflected image of ABC over the line of reflection if flipped over. Each point traveled perpendicularly to the other side of the line of reflection. It is messy. We're going to translate this triangle along this vector, which is just a directed line segment. It's just a line segment with direction. So I'm going to come over here and I'm just going to measure This is how many units I'm translating. I'll go over to L first. Using this distance, I'm going to swing an arc. So I measured that from here. I'm going to go over to the other end of the vector. Oh, I didn't make my first arc long enough. I don't see an intersection, so I'm going to go back over here. And I'm going to extend. And that way I get the direction in there too. And that's L prime. Because it went in a slanted direction. So this way ensures that we're getting the direction. We'll do it one more time. Gonna measure, make sure I have the length of the vector. Okay. Next point, point P. I'm gonna go over the point P. And I measured like this. Point P. Arc, or you can make a circle. I'm just tired of all these circles. Over to E. Oops, oh no, that wasn't good. Okay, try that again. Back over to E. Once again, I'm tired of making all these circles. So I'm just making parts of circles. And that's where P prime should go, the same distance as NE in a slanted direction, in the same direction. And then finally, the last one is A. Same vector measurement. I'll make a circle because I don't want to miss the intersection for this one. And then finally, we'll connect everything together. I did a really bad job of connecting that.